Okay, so limiting and excess reagent calculations. So we're now going to be able to fill out the whole ice table. Now, I kind of emphasize the ability to complete the whole ice table. When you start working through questions, you don't necessarily have to fill it all out, but we'll have those skills to do that. Same as before, the limiting reagent will be 0 at the very end. Okay. The excess reagent will not go to 0, and we'll start figuring that out. Okay. So in my first example, determine the mass of precipitate when 1 1/4 moles of sodium chloride is mixed with 2 moles of silver nitrate in 100 mils of water. Okay. And typically on a test or quiz would make you balance, predict the reaction and balance it. So we have sodium chloride, which is an ionic compound. We have silver nitrate, which is an ionic compound. So that would lead to a double replacement reaction, and I've done that already. And all of the ions are +1 ion. Okay, I always choose to organize my stoichiometric questions in a nice table. Okay. Normally the first step is calculating moles, but I've given that to you right in the question. We have 1.25 moles of sodium chloride. And silver nitrate is 2.0 moles. And now we have to figure out which one runs out. Now, it isn't necessarily always the lower number runs out first. Okay? We have to look at how fast they run out and in what ratio they start running out. Okay? And the ratio, or how fast they run out, for every 1 sodium chloride that reacts, we're going to get 1 silver nitrate to react. Okay? So these are going to react in equal amounts. So they'll both react 1/4 mole together, then they'll both do 1/2 mole, they'll both do a whole mole, they'll both do a whole mole and 1/4. And in this case, once 1 mole and 1/4 of both react, the reaction will have to stop because we'll run out of we'll run out of sodium chloride. Okay, so when the reaction is a 1-to-1 ratio, now that 1-to-1 ratio I'm referring to is 1 of one reactant to 1 of the other. So when the reaction is a 1-to-1 ratio, I'm going to leave out of reactants the lower mole reactant is a limiting reagent. So the lower amount one is our sodium chloride. That's going to run out first, and the silver chloride is the one that'll have the excess. Okay? And now we can pretty much go back to what we did before. These 1-to-1 reactions, students have a lot of success. They're not that complicated. The lower one runs out first. So limiting reagent, that's still the one that goes to 0. All of this 1.25 moles is going to react away. Okay. Okay. Once you know a C value, you can fill in all of your C values. The C values, the changes always follow your stoichiometric ratios. 1 sodium chloride reacts with 1 silver nitrate, makes 1 sodium nitrate, and 1 silver chloride. They're all the same stoichiometric coefficient, so all our changes are going to be the same number. The two reactants go down, and our products go up. Now I have left moles units out of my products because I'm running out of a bit of room to line things up. Okay. Now both products would start at 0. Okay. And then we can take what we start with and add or subtract the change. Okay. Now in this question, we only really cared about the precipitate. What mass of precipitate would we have? So there's my precipitate. That's the column that I really need to fill out. I'm going to fill them all out to show that you can, but then you would just care about the last one. So the silver nitrate, we start with 2 moles, we react away 1.25, so there will be 3/4 of a mole left over. Sodium nitrate, there'll be 1.25, and silver chloride, 1.25. Okay. I'm not going to finish the number part of this. I want to keep moving on, but the question does ask for mass of silver. It asks for mass of the precipitate, which is silver chloride, and mass is moles times molar mass. And that's what I would need to do to finish this question. I just didn't pre-calculate that out. But I wanted to show you when you have a reaction that has one reactant reacting with one reactant, find the moles of both. The lower one is the limiting. Questions about that one before I do another reaction that will also be a 1-to-1 ratio? It doesn't get carried because not all of it reacts away. At the end, there'll be no sodium chloride left, but silver chloride, not all of it needs to be consumed. Now, is your thinking that there's still some of that silver ion left over? Or do you want to, rephrase your question maybe for me. Oh yeah, I see what you mean. You're thinking it's only going to, yeah, don't, yeah, yeah, I guess how you'd be thinking that way, but that's kind of not what happened. Both the sodium and the chloride are only going to have 1.25 moles react. Don't apply that 1.25 to the pieces after they split up. Just use sort of how it's been laid out to make your predictions. Like if you look at the chloride part, all the NaCl is going to react. 1.25 moles of chloride reacts. I'm just going to write on the board. Okay. So all the chloride is going to react away, and then we see all of the chloride showing up in the silver chloride. Yep. Yeah. Okay. It kind of does. Your thinking is right, but we're tracking it in 2 places. So yeah, I'm going to show you how you're actually right. It's just presentation. If you just think of the nitrate piece, okay? If you think of nitrate, at the end, there is 1.25 moles written as the product, but we have 0.75 moles left over from the reagent. If you put those two pieces together at the end that both contain nitrate, you get that 2 moles that I think you're expecting. It's just we've written it separate. At the very beginning, if you look at your 2 nitrate pieces at the beginning, there's 2 moles in total, 0 and 2. If you look at your nitrate at the end, it's just now broken up and we're writing it separate, but there's still the 2 moles. Does that kind of make sense of what you're thinking? Yeah, the 2 moles, okay. So you weren't wrong in your thinking, I'm just not writing it out that same way. Okay, so this second example is more typical of what you would get on a test or quiz. We don't tend to give you moles, we tend to give you concentrations or volumes or masses. Okay, so we're going to have that typical extra step of we have to calculate moles. Okay, now I'm going to write everything in my ICE table in moles. I tend to run out of room, so I'm just going to label my units next to my ICE table and leave them out, and then everything will fit in the columns nicely. Okay, so sodium chloride, I need to know how many moles is there, and then I'll have to figure out silver chloride. So I'm going to do some mole calculations. So I'll start with NaCl, and moles from a pure substance is mass over molar mass. So sodium chloride is 10.0 grams divided by the molar mass for sodium chloride, 58.44 grams per mole of sodium chloride equals 0.171 moles. So I had to do some work to get my moles. Now, is everyone seeing my pen? I looked at my video from a lesson yesterday and I found that the pen looks big to me, but on the video it looked very small. Is the pen thickness fine? Can you see my writing clearly? Okay, good. Sometimes when I look at my videos, it's when I see your perspective. Okay. So now I got to repeat this with silver chloride. Sorry, silver nitrate. How many moles of it do I have? So AgNO3. Again, it's a mass that we're given of a pure substance. We want to use moles, mass over molar mass. It's 10 grams again. Okay. And silver nitrate is much heavier per mole, 169.87 grams per mole. Okay. So the 10 grams of silver nitrate, which is in red, is much less moles. So now I have my 2 moles, so now it's just like the previous slide. Okay, this is another one of those reacts with one of those, so the limiting reagent will be the smaller number, and that's the red silver nitrate is the smaller number. Okay, these are both going to react at the same rate because they have the same stoichiometric coefficient, excess reagent. Okay, so the limiting is going to go to 0, the excess will not. So all of that original red moles will react away. Okay. Now in this question I just said let's fill out the whole ICE table. So I can fill everything in. Okay. The first thing, I think it's really good to do all the C lines. You don't lose track of the stoichiometry. Okay, again, the stoichiometric ratios show up in our C lines. All the coefficients are 1. So all of the changes will be the same. They're all going to be 0.0589. The reactants go down by that amount. The products go up by that amount. Okay. I'm not doing required over given because the required to be a 1 coefficient, the given would be a 1 coefficient. So I'll do my products first because that doesn't require any calculation. Again, I have no units in my table, but moles are the units for my whole table. And for my one missing excess reagent, a lot of it is left over. And that's a full ice table completed for the 10 grams of each reactant. Okay. Now I never use this 100 mils. It's a distractor. It's a solvent. You have to dissolve those masses in some amount of liquid, some solvent, because if two solids don't react with each other, if you just dump them together, they need to be dissolved, and then the aqueous solutions will react. But two solids are often not very reactive with each other. So don't let total volumes distract you when they give you a pure substance at the beginning. Okay? Where concentrations will tie in, and when we get into mixed stoic, is if you wanted a concentration, you need the moles and the volume. You get the moles from your ice table, and you get the volume from the question. Okay? So next, in my last example, is calculations when the ratio isn't 1-to-1. Okay? So we're going to have to do a bit more work to figure out which one's going to run out. I'll just uncover the whole question. So my question at the top is, what is the amount of the excess reagent? And there's a second question, what's the concentration of salt? Okay, I want to start leading into some solution stoic and pull in our solution skills with this question. Okay. We're given some data. There's a little over 3.5 grams of hydrogen chloride, and there's a little under 6 grams of calcium hydroxide. Okay. Now, if you take those two binary compounds, okay, the first one is an ionic, but it's still a binary substance, you're going to get a double replacement reaction. And I did that and balanced it, and it's not 1-to-1-to-1-to-1. So the smaller moles of the reactants isn't necessarily the limiting. Okay? And I'll go through how to figure that out, but we have to get moles. Okay? So same as the previous question, I need to do a couple mole calculations. We have solids, okay, pure substances to calculate moles from. Okay. So I will start with HCl. Moles is mass over molar mass. Okay, so this is the solid before it went into solution. 3.65 grams divided by the molar mass of HCl. 36.46 grams per mole. Okay, my grams cancel, and you end up with just moles and 1.00 moles. 0.100, and again, there's my units. Second calculation, calcium hydroxide. And I really encourage you, I know you're online right now and you're going to be doing tests online and I don't see your work, but I really love when students put a little heading above their written work. So everybody will be taking Chem 30, and often students will just start calculating moles, and as a teacher I'm not sure what calculation they're doing, but once I see a header or a heading, HCl, I know exactly what you're trying to do, and if you make a mistake I can figure it out so much faster. So calcium hydroxide was 5.56 grams divided by its molar mass, so 1 calcium, 2 O's, and 2 H's. 75.09 grams per mole. We get 0.0750 moles. Okay, and now we've got to figure out which one is going to run out first. We've got less calcium hydroxide, but we've got HCl reacting twice as fast. So somehow we have to figure out, if one's reacting twice as fast, 2 units of HCl are going to react with only 1 of calcium hydroxide. Okay? Now a sort of quick way to figure out which one's going to run out first is to scale both moles by their stoichiometric coefficient. We're kind of dividing away how fast they react. Okay? So I'm going to call this, what is the limiting reagent? Okay? And to figure this out, I take the moles of each reactant and divide it by its coefficient. So there's 0.100 moles of HCl, but it's going to react away twice as fast as any one coefficient amount. Okay? Calcium hydroxide is 0.0750 moles, and it's going to react at a rate of 1. It's going to react slower. Okay? And by doing this, I'm factoring in how fast things react. And now whatever ratio is smaller is the limiting reagent when I factor in the speed of it reacting, or the ratio. So we get 0.0500 moles per 1 unit reacting versus 0.75. Okay. And now the lower one is the limiting reagent. Okay. When I factor in the fact that HCl reacts twice as fast, it only has the equivalent. Of less moles to react away. Okay. Again, now we don't use any of this numbers in what is the limiting reagent. Don't use any of those numbers, but they tell you which one's going to run out first. Okay. Okay. So the fact that HCl reacts twice as fast, there isn't enough with it reacting twice as fast to use up all the calcium hydroxide. This is going to be the limiting reagent. Okay. All of the HCl is going to react away. All 0.100. Okay. Now, if you ever make a mistake with predicting the limiting reagent, you'll end up getting a negative number for the other chemical, and that would be a hint that you made a wrong prediction. Okay. So I'm going to pause there for a second, and again, this is sort of the hardest part of the unit, and if you're good with this, you'll be good with the unit, but again, I'll pause for 30 or 45 seconds. So if there's no questions, I'll keep going and solving this question. Everything's going to be the same as before now. We know what's limiting. We just don't have all 1. So we're going to have to do some doubling or halving. Okay. We know, again, our stoichiometric coefficients. We'll see their ratios show up in the C line. So to get calcium hydroxide, we're going to multiply by its coefficient, which is a 1. And divide by the coefficient of HCl. That's the chemical we're starting with. So that's going to be multiplied by 1/2. So we're going to have to subtract. If we look at our first product, that has a coefficient of 1. So multiply by 1, divide by 2. I'm using that red change as my starting point. So that's a product going up, 0.0500. Last, I'll pick another color. Please let me know if you can't see yellow. So multiply by its coefficient for water is 2, divide by the coefficient of the red number where I started. That's also a 2. Okay. Now, as you get better, you won't even do this math. Anytime you see numbers with the same coefficient, they'll always have the same change. Okay. Okay. So our red change for HCl is -0.1, and for HCl, we're going to make 0.1. Products would start at 0. And our excess reagent is working out. We're not getting a negative number. If we take the black 0.075 moles, we subtract away 0.050, we're left with 25 millimoles, or 0.025 moles. So I filled out the whole ICE table for practice. I'm going to scroll up and look at the question and answer it fairly quickly. Any questions about what I did before I finish this one? Which change, or which chemical are you? HCl. Underneath the table? You're asking about that too? Sure. This one? Yeah, I'm always taking some C number and I multiply by the required coefficient and I divide by the given is what I've been doing over and over again. So the number would be like this change value, and I want to convert that change into another chemical's C or another chemical's change. I multiply by what the required coefficient of what I'm trying to figure out. So if I do, how do I figure out this double underlined green number? Okay, I'm going to take the red 0.100, multiply by the coefficient what I'm trying to figure out, which is a 1, and divide by the coefficient of the given, and the given red is coming from a 2 coefficient. And that's what I've been doing all along. Now, you can not even turn this into math or formulas. If you look at HCl, the change for calcium hydroxide is half as much. 1 is half as big as 2. Okay? And students can just sort of do this by inspection if they want. HCl has the same coefficient as water, so their change will be the same. So if the coefficients are doubling or tripling, that's what the C is going to do. Okay? If you're trying to turn it into a formula, it's take your number and your change, multiply by the required coefficient, divide by the given coefficient. Okay? And this certainly is a section that it's best if students practice, and then I will do some full examples. I'll have some examples ready in Thursday's tutorial, and I'll do those examples and post them online. A fair number of students see this lesson and they need more practice and more examples. So I'm sure there's many out there who get this a little bit and you need to practice, and no, Thursday I'll do some more. And I'll also, I'll do a mixed stoic example for you. Okay. So I'll finish this off and then let you know where you can start practicing. When I say finish this off, what was the actual question? And they asked for the mass of the excess reagent, which we did, but we haven't done that concentration part. Okay. So concentration of the salt produced. Okay. So concentration is moles over volume, and we have to use, or volume has to be in liters, and let's see, what's our salt? Okay. Well, we got two products. We got calcium chloride and we got water. Well, water is definitely not the salt. This ionic compound is a salt. Okay. Anytime you have this is actually an acid reacting with a base, making a salt and water. So calcium chlorides are salts. So we have 0.0 0.500 moles of our salt, of our calcium chloride, and we have to divide by the volume, and it has to be in liters. Or that's how we express amount concentration. I didn't say that fully in the question to do amount concentration, but that's the typical scientific way. 100 mils of water, so I have to convert that to liters. There's 1,000 milliliters in a liter. And this will give us our amount concentration. And that's our concentration of our salt. So for practice, there's some questions in the textbook, and a lot of students, if you have your paper workbook at home, a lot of students like working in that, and page 83 is filled with limiting and excess reagent questions. I just didn't go through, and please omit, okay, any gas questions. Now, I think page 83 doesn't have any, but as you work your way through the workbook, and on D2L, I'm going to post a whole bunch of pages that you can practice between now and next Tuesday, because Thursday is just a tutorial. Please don't do anything where they give you pressure, volume, and temperature. Okay, we didn't do our gas stoic unit, so those you won't be able to do, and they're not very important for Chem 30, which is why I'm taking my time on this unit, which is super important, and not spending time doing gases. It's just not good time management. Okay. Now we'll end with a little recap of all the ways to calculate moles from all the units in this course. Okay, this will be very handy as you start working your way through over the next week. If something is pure, and that's what we've been doing so far, you can get moles from mass over molar mass. Okay, when something is pure, it could be a solid, could be a liquid, or it could be a gas. Okay, it just can't be a solution. Okay? Sometimes students think this only works with solids, and that's not true. You can have 10 grams of methane, which is a gas. As long as it's pure methane, that works. Okay. For solutions, okay, you get moles from concentration times volume. Okay. So you'll be doing one of those two techniques. What we skipped, which is what you use for gases, and we didn't do the ideal gas law, where pressure times volume equals moles times a gas constant times temperature. So moles is PV over RT. But it's not, I'm not going to go through and try to do a quick demo of these. We're just going to skip using that. Okay. So you're just going to get tested on pure substances and solutions, okay, of which I haven't assigned solution stuff yet. So I can, if you want to go